Okay, everybody, welcome back. I see our class is getting smaller as we progress through the semester. Okay, got one more. Okay, just a quick rehash. We are on chapter 5. Our plan is to finish that up today, finish chapter 6 today. It's a fairly short one. And then we got coming soon is another exam number 2, which is we'll cover chapters 4, 5, and 6. Okay, similar format. Then exam number 1. Okay, any questions before we continue in our voyage here in chemistry? All right. Well, let me start off where we ended up. We were then talking about the orbits. And we rehashed through fresher memory. We went back and talked about these electrons, and it was determined that these electrons, or proposed that these electrons exist in specific energy levels, specifically 7 energy levels. So we have 7 periods on our periodic table. All right, period 1, period 2, period 3. Now, further into this theory was developed that within the energy levels, there were sublevels, which are called orbitals, okay? There are 4 types of orbitals denoted by the letters S as in Sam, P as in Paul, D as in David, and F as in Fred, okay? Those are the 4 different types of orbitals. Now, there's only one orbit for the S, one orbital for the S. There are, however, 3 of them for the P in the 3-dimensional X, Y, and Z. And those are denoted by, we're denoting those by the box. The box here represents the different orbits. So let's look down here at the bottom. And so there's one S orbit, okay? And then there are 3 P orbits. And then there are 5 of the D orbits. And then there are 7 of the F orbits. Now, every orbit can handle a maximum of 2 electrons. And so that means that the max number of electrons for each orbit are 2 for the S, okay? For the P's, the max number is 6 because there's 3 and each one can handle 2 electrons. The D, there are 5 D orbits. Each one can handle 2. So we have a maximum of 10 electrons for the Ds. And then you can see with 7 F orbits, we can handle a maximum of 14 electrons. Okay. All right. And so we have this diagram here to demonstrate that as we move up, down, I should say, the periodic table. So basically, if you have with you the periodic table with you, you will see that level 1 encompasses hydrogen and helium, okay? And then level 2 energy level is the far left, element number 3, starts off with lithium all the way across to neon. Okay, energy level 3 starts off with sodium on the periodic table, goes across the periodic table to argon. Okay, and then period 4 starts with potassium and goes all the way across to krypton. And that's what we're doing here when we start filling up electrons. We start off with the first energy level, and then we start adding electrons to each of the orbits, okay? Now, all these 7 energy levels have the S orbit. So you will find 1S, it will be denoted by 1S. The 1 tells you it is the first energy level, or there'll be a 2S, then telling you that's the second energy level, 3S, and etc. okay? Now we incorporate a superscript to the orbit letter, okay? And that superscript depends on the maximum number of electrons that each orbit can have. So we know that the S, we can have two superscript S superscript 2, meaning there are 2 electrons in that first orbit. And the P, there's a maximum of 6 electrons, so it's superscript 6. So the numbers can vary from 1 to 6. For the S, the number can vary from 1 to 2. And the D, the number can vary from the superscript can vary from 1 to N, and the F 1 through 14. Okay. Then we put the number in front to designate which orbit, which energy level we are at. So everybody has S orbits from 1 through 7. We got 1S, and then we got all the way down to 7S. Okay. The P orbits don't come into play until we reach the second energy level. And then the D don't come into play until we reach the third energy level. And then the F orbits come into play at the starting at the fourth energy level. Okay. All right. So with that in mind, we can start working up the periodic table of the elements to start off with hydrogen. Okay. Hydrogen has 1 electron. It's the element number 1. And so for hydrogen, we're going to write what is called the electron configuration, which is the coefficient number 1 in this case, and then S to designate first energy level, the very first orbit. One final thing. Within the energy levels, whichever level this is starting at 2, the order of filling up the orbits are S fills up first, okay? Then the P's get filled up, then the D's, and then the F. So that is the hierarchy, that because what's happening is the S orbitals are at a little bit lower energy level than the P's. So the S get filled up first, okay? Then the P's, then the D's. All right, so let me clear this up. And we start off with hydrogen. Hydrogen has 1 electron, element number 1. Okay, and so to write its electron configuration, we simply put 1s and then superscript 1. Okay, we show that in this box by drawing an arrow. Well, this arrow represents that electron. So notice there's 1 electron in that box. Go across the periodic table to helium. Helium has 2 electrons. And so now we can substitute that 1 for a 2. And we show that by another arrow. And I put that in opposite direction. This is beyond the scope of Chem 130, but basically what this tells you about having the arrows go in different directions, that within each orbit, where it has 2 electrons, the requirements of the calculations so forth mean that 1 electron goes in one direction, that means the other one goes in the opposite direction. So that's what's being said here. So that right here would be the electron configuration for helium. Okay, helium has 2 electrons. Okay? All of those electrons occupy the first energy level, and for helium, those 2 electrons occupy the s orbit, and hence we put a superscript s. Okay. Now, once we go around to element number 3, which is lithium right here. Element number 3 tells us we have 3 electrons, okay? So for lithium, we fill up the first energy level, 1s2, and then we have to go to the next energy level, which is in the second period, second energy level. And then the orbit is the S, because that gets filled up first, okay? And so then there's 1 electron. In that, of the 3 electrons for lithium, 2 of them are in the innermost energy level, in the s orbit, And then the next one is in the energy level number 2 in the outermost layer, which is energy level number 2, and it is in the s orbit. Okay. Now, when we move over to beryllium, which is the next one, we simply replace that 1 with 2. Okay. And I put another arrow in. Beryllium is element number 4, 4 protons, 4 electrons. Okay. 2 of those electrons are on the 1s2 orbit, and the other 2 are in the outermost shell. We call that the valence shell, the outermost shell. 2 of them occupy the s orbit. Okay. Now, keep in mind, if you got the periodic table in front of you, we've been going across the periodic table. So those first 2 columns, Roman number 1a and 2a, you can start thinking of those as the S block elements, okay? S block, because there are 2 columns, S1 for the first block, S2 for the second block. Now we're going across the periodic table, starting with boron, which is in group number 3a, okay? At that point, there should be 6 columns all the way from boron, number 5, across to neon. There should be 6 columns on the periodic table. And those 6 columns, think of those as the P block of elements. And specifically, the first column would be P superscript 1, next column over P superscript 2, and so forth until you get to the last column, which are the noble gases, and you have P superscript 6, okay? All right, so this is boron. Now, we enter the next element, which would be boron, okay? Boron is element number 5, and its electron configuration is as follows. We're 1s2, okay, 2s2, and now we enter the P block elements, okay, starting with number 5. And so it is still in the second energy level, and we're going to introduce the P electrons, and it'll be P superscript 1. So this will be 1s2, 2s2, 2p1, represents the electron configuration for boron. Okay? And quite obviously, we go over to carbon. Okay, carbon, we have 6 electrons total, all right? So now we just keep adding to the P. Notice that I put the next arrow in the next block. Again, we fill the blocks up first with single arrows, single electrons, until they're all full, and then we start doubling up. So that's carbon. So then we go to nitrogen, which is the next one, okay? And that P2 now changes to P3, and that's the electron configuration for nitrogen. We go to oxygen. Okay, now we can double up those other electrons, get rid of, erase the 4, and that becomes 4 superscript P superscript 4. There are 4 electrons for oxygen in the p orbit and 2 in the s orbit, okay? All right, and then as we continue, just continue all the way across till we get to neon, and we fill them up, okay? And so now the electron configuration for neon would be 1s2, 2s2, 2p6. Neon is element number 10. It has 10 electrons. Of those 10 electrons, 2 of them occupy the innermost energy level in the s orbit, which is the 1s2. And then the other 8 go into the second energy level. And starting with the s orbit, and that gets full, okay? So the 2s2. And then we go all the way across to the other 6. And remember that we can put 6 total electrons for every p, right? So if you look at this, its outermost shell for neon is in the second energy level. Point number one. Point number two, there are a total of 8 electrons in the outermost shell, okay? The driving force for all chemical reactions that we're going to soon learn is to get to that, quote, magical 8, get 8 electrons, and that's due to the mathematics of the model and so forth, okay? But that's for us here at Chem 130, we're striving to get to 8 electrons around the outermost shell because that is the most stable condition an element can have. And that is why the noble gases are very unreactive because in their outermost shell, be it in the, for neon, which is the second energy level, for argon is the next one down, energy level number 3, and so forth, okay? All of them have in common 8 valence electrons in the outermost shell, okay? And that magical 8 is the stable form. And that's why noble gases are very unreactive. And for helium, its magical number is not 8 because it doesn't have 8 electrons to deal with. It's 2. Its outermost shell, the 1s2 orbit is full, okay? But all the all the other noble gases have 8. 6 of them are in the p orbit, and the other 2 are in the s orbit. That coefficient up front can change depending on what energy level they're in, okay? But all of them have 8 of them. Okay. Now, once we obtain that, if you go from neon and you go around to the next element, you have sodium, right? And so sodium has 11 electrons. And so sodium has all what neon had, 1s2, 2s2, 2p6, but now this is for sodium, okay? Sodium's in the third energy level. We'll look at your periodic table, find out where sodium is, okay? And count the pearls from top, it's in number 3, okay? So that'd be 3s1. It is in the first column, period number 1a, so that is the S block, and hence we have 3s1. That one electron has 11 electrons, okay? And all of them except one are in the innermost shell. The 2 of them in the energy level number 1, and 8 of them in energy level number 2. And then all out there in number 3, you have the 1 electron in the s orbit, okay? And that is true for everybody in that column. They have 1 electron in the outermost shell. What's different between each element is what energy level they would be. They could be either in the first energy level, second, third, fourth, fifth, or sixth, but all of them have that in common. And that's why they react very similar, because they have the same number of valence electrons. And that's where all the action happens, you know, as far as chemical reactions is in the outside layer, okay? So that continues. We can go all the way across the periodic table. And it's basically a sequential step of filling up the electrons in a specific order and specific energy level. And that's what we're doing here. This is to demonstrate here how that is occurring and where these electrons are going with respect to the orbit and the energy level that they're in. Now, keep in mind that these orbits that we have been talking about are mathematical equations. They come from the area of science, chemistry, physics called quantum mechanics, okay? A lot of that work was started and began in the early 1900s and has been over the years, you know, fixed up and, you know, gotten better, and it's still at this point in time tells us or represents what nature's is happening with respect to the chemical aspect of it. So quantum mechanics is still holding its ground with respect to the model that we have of these compounds and elements, okay? So the first orbit, the s orbits, when you plot that data, when you plot data on that equation that comes about, and these are very sophisticated equations, you get an image that looks as that. It's three-dimensional X, Y, and Z. In that area, if we were to do a cross section of that, you wouldn't see much of that blue within the center. But that blue represents where there is a probability of an electron being in that particular area in space. Okay. Now for the p orbital, there's three of them, as I stated earlier. And the three of them come in three different directions, X, Y, and the Z axis. And their shape as follows. Again, there are three separate equations, data is plotted, and you come up with these three images. These are called dumbbell shape, okay? Now, with respect to the other orbits, they get very crazy looking, very crazy looking. So, excuse me, you can see the top one that represents the S orbit. Keep it in mind, you go from 1 to 7s. So everybody has, all the elements have an S orbit, okay? You start out with the 1s could be maybe the size of, relatively speaking, the size of a golf ball, and then 2s could be maybe a baseball, 3s could be maybe a softball, etc. Okay. Then we get the p orbits, which begin in the second energy level. So there's no p orbits in the first one, but just in the second down. So we get 2p, 3p, 4p, etc. Then we have the d orbits, and you can see the shape. There's 5 of them. Very interesting looking. Five of them. Those are the ones listed in blue. And then the 7f orbit. Okay, 7f orbits. Keep in mind that each one can handle 2 electrons. And they get very, very wild looking here. That's the result of the mathematics involved with respect to quantum mechanics. Okay. Anyway, now I went through an explanation as how we were filling up the electrons for the elements as we went down the periodic table. All right. All that is shown here in this particular graph, where the order begins with 1s and then goes on 2s, 3s, etc. Okay, it's denoted here. Now you have the choice. You can memorize this or use this as a reference point. Okay, and use this graph, and that's fine. There's nothing wrong with that. I prefer to use the element on the periodic table and their relative position on the periodic table to very quickly write out the electron configuration, okay? So we're going to talk about both of them. So, the first method is just simply remember what the sequence is given to you here in blue, okay? So, for example, if we do that, we want to do carbon. Okay, carbon, we know contains 6 electrons. Okay, so the very first orbital is full with 2 electrons because there's only the s electron orbit. So it's 1s2. Remember, the superscript is the number of electrons. That energy level is full. Then the other ones have to go into the second energy level, represented by the number 2 here. That's the outermost shell. And then there is the s orbit in the second energy level. That gets full first. So we have maxed out the s orbit, 2s2, and then we spill whatever's left into the p orbit. So in this case, there's 2 less, so it goes into the 2p2. Okay, and we can use that sequence given in that graph to get to that point. Okay. Or we can quickly use the periodic table to get us to the electron configuration. Okay, now let me rehash this. The first 2 columns, think of those as the S block. okay, the S block of elements, okay? Starting from here, Roman number 3A to Roman number 8A, think of those as the P block elements, okay? And note there are 6 blocks, so that would be P1, P2, P3, P4, P5, and P, oh, whoa, that's a 5, not a 6, and P6 if we went across. Here, this would be S1, S2. And then these guys in here, think of those as the D block elements. You will notice that there are 10 columns here, so we can go D1, go across to D10. And then these guys here, think of those as the F, where you go from F1 across to F14, okay? Now, keeping that in mind, you can very quickly, oh yeah, mark your periodic table with the energy levels. 1, 2, 3, 4, 5, 6, and 7. So with that information, you can literally get the electron configuration for most any one of these elements. Let me go back and do carbon again, like we just did. Okay, carbon is right here. Okay, well, if we look at this, carbon occupies both the first energy level and the second energy level. Okay, second of all, it's in carbon is in the P element, in the P block. It's in the second column of the P block, so I can very quickly know that's P2, okay? Furthermore, I can say, put a 2 there to help me real quick, because I know it's the second energy level. So quickly I can go, all right, so the 1s2 is full, because that's going from here all the way across, okay? Then I go into the 2s2, that fills up the first 2 columns, and then I know that I'm in the second column of the P. So I go 2P2, okay? And that is the electron configuration for carbon. If I want to go to, say, fluoride, no big deal, I can change that 2 to 5. There it is, 1s2, 2s2, 2p5. And then go to neon, and then that 5 becomes 6, okay? So knowing its position on the periodic table quickly determine the electron configuration. All right, let's do one more. Okay, let's do potassium, okay? Well, thing to note is potassium is in the 4th energy level, which means that the 1, the 2, and the 3 are full, okay? It's got 19 electrons. And so those 18 are going to be in the innermost energy levels. It is in the first column of the S block. And given that it's in period number 4, that tells me that in the outermost layer, that would be simply 4s1, okay? 4s1. So now I can quickly go fill up the electron configuration. 1s2, that's full. Then we go into the second energy level, which incorporates the S and the orb and the P. So that's 2s2, 2p6, okay? Then we're down with the 3, it should be 3s, P, and 3p6, because we went all the way across here, okay? And then finally, the last one is 4s1, okay? And that's very quickly the electron configuration for potassium, okay? For potassium. All right, now the confusing part that can occur is when we get into the D electrons. Well, I'm here to tell you, you don't have to worry about the D electrons until you start off with element number 21, okay? Once you hit 21, its D electrons come into play. However, the d orbits for those elements in the fourth energy level come out not in the fourth energy level like the S and the P, but actually come in one less energy level than the energy level it's in. And so for number 21, it would be 3D1 for that D electron. Notice that number 21 is in the fourth energy level, and you would think, okay, well, it would be 4D1, okay? But that's not the case. It turns out from the mathematics of it that the d orbits are one energy level in than the energy level that they're, let me restate that. For the d orbits, their energy level for the d orbits are one energy level less than the energy level that they're in. So S number 21, its d orbits begin in energy level 3. And that continues all the way across to zinc, where this will be 3D10. There's 10 columns here, 3D10. Okay. Plus everything else, 1 through 4. Okay, will be there. And then for the F block, I should say, their F orbits come into play 2 energy levels less than the energy level that those elements are in. And so this would be 4F1 for number 59, going across to 4F14, okay? So for the d orbits, their energy level is 1 energy level less than the energy level that element is in. And for the F elements, their F block or the F energy level are 2 energy levels less than the energy level that they're in. Okay, this one here, they are in energy level 6 and 7 respectively. Okay, but the F orbits are start off at the 4th energy level. And so for here, number 92, it would be 5F1. Okay. 3S1 for number 21. This would be 4D1 here, 5D1 here, etc. Okay. And I have another slide that will show you kind of put everything together. The thing about going in the D block for us in Chem 130, we're going to just name them sequentially D1 first column to D10. Okay. And the same is true for the F block, where they're filling up will be F1 to F14. We'll see in the slide that I have that they fluctuate a little bit. Again, that's beyond the scope of Chem 130, and it's going to be simply a straightforward sequential filling up of that orbit. Okay. Now you might ask, why are we doing this? Well, the purpose, multiple purposes, but the main purpose is to give you a perspective of the electrons for those elements, and specifically the outermost electrons, okay? Because knowing how many they have in the outermost electrons will tell us a couple of things. One, depending on the number of electrons in the outermost shell, it could either gain more or lose what they have. To get to that stable state of having 8 electrons around the outermost shell, okay? We'll shoot some examples here in a bit. That is the driving force. The metals will lose electrons to get 8 around it, and the nonmetals will gain electrons to get 8 around them to get into a more stable state. Okay, we talked about this at length. We'll just go on. Now, here's what I was mentioned earlier about think about the S block, if you will, the D block, and the P block, because we have S1, S2, two columns for the S block, which are listed in blue. We got P1 all the way across to P6 for the P block elements, and then the D blocks starting at D1 all the way across to D10. Okay, and then we got the F1 to F14 with respect to the F. Okay, and that kind of helps us out with figuring out the electron configuration relatively quickly by knowing the position of the element and where they're at. Okay, so to do the electron configuration, we can very quickly figure it out. Okay, let's do sodium. All right, well, sodium is right here. Okay, and 1, 2, and 3. It is in the third energy level. Okay, being in the third energy level, I can very quickly go 1s, 2s, 2e, and then 3s. Now, why do I put 3s? Because it's in the first column of the S block, right? And even more so, I can go 3s1. So that takes care of one electron very quickly. Sodium has 11, so we got 10 more to go. And the only place they're going to go will be obviously the 1s2, the 2s2, and the 2p6. So add up all of the electrons that sodium has, you should see 11 of them. One of them is in the third energy level in the S orbit. The other 8 of them are in the second energy level, of which 2 of them are in the P orbits and 2 of them are in the S orbit. They have 8, and then the final 2 are in the innermost layer, the 1s2. Okay, see how quickly we made the electron configuration for that, just based on their position on the periodic table. All right, let's do oxygen. Okay, oxygen is right here. Okay, oxygen is in the second energy level. All right, so oxygen has 8 electrons. 8 electrons. All right, and it is in the 1, 2, 3, 4th E block, E to the 4th, and it's in the second, so it's 2p4. So we can go quickly write it down. 1s2, 2s2, 2p, and 4. Okay. So count your superscripts. I got 8 electrons, which is consistent with the number of electrons that sodium has. Okay. All right. Let's do one more. We're going to do all of them. Here's calcium. Find calcium. Calcium is right there. Okay. Calcium is in the 1, 2, 3, 4th energy level. Okay. Second of all, it's in the S2 block of the 4th energy level. So we can quickly write the outermost layer for S2. Okay. And so the 1, the 2, and the 3 energy levels are full. So we got 1s, 2s, 2p, 3s, 3p. Okay. So we just put in the superscripts. And that should add up to 20 electrons. Of those 20 electrons, 2 of them are in the outermost shell, which is the 4th energy level. Okay? Outermost shell. Remember, that's true for everybody in that group. They all have 2 electrons in the outermost shell. Okay? All right, now we got chlorine, which is right here. Chlorine is in the 1, 2, 3, 4, 5 block, the 5th column of the P block. It is in the 3rd energy level. Okay, 1, 2, and 3. So that last is 3p5. Okay, so I got 3p5 for the outermost shell. And then the others are full. 1s2, 2s2, 2p, 6, 3s2. Okay, and that is the electron configuration for chlorine, which has 17 electrons. All right. Okay, here's the 1s2, and then 2s2, 2p6, and 3s1. Okay. Oxygen, which is right here, means that the 1 and the 2 energy levels are full. So 1s2, 2s2, 2p4. Okay. And then calcium, we did that. 1s2, 2s2, 2p6, 3s2, and then 3p6 and 4s2. Now bear in mind, keep in mind, when you write these out, the number is a coefficient, okay, so that's a big whole number there. And then you got the letter lowercase, but you have the superscripts. I lost my train of thought. Something was caught my attention here. It'll come back to me. Okay, now we got chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. Okay, 3p5. Now, the big takeaway here is this. When we talk about the valence shell, that is the outermost layer of each of these elements, okay? For sodium, it is the third energy level, and there's 1 electron sitting, okay? For oxygen is the second energy level, and there are a total of 6 electrons in the outermost shell. For calcium, it is in the 4th energy level. There's 2 electrons there. And then for chlorine, there are 7 valence electrons, 5 of them in the P, 2 of them in the S. Now, if you look at the group that each individual belongs to, okay, sodium is in group 2A. If you look, you find sodium, oh, excuse me, what am I saying? 2A, it's 1A. The 1A right here, okay? That 1A tells me I got 1 valence electron, which is the 3s1, okay? Oxygen is in the 6, Roman numeral 6A, okay? 5Vi6, V6A tells me there's 6 valence electrons, okay? Then we got calcium, which is in the 2A. That's why I was looking at calcium and thinking sodium. And then chlorine has 7 valence electrons, and that is the group it belongs to, 7A. So that group number on top for the A elements, the ones with an A, tells me at a glance how many valence electrons for everybody in that group, okay? For everybody in that group. And that explains why everybody within that group reacts very similar, because they all share that property of having the same number of electrons in the outermost shell, okay? All right. This is also going to explain what's going to happen here is why metals want to lose electrons and why non-metals want to gain electrons. Now think about this. Look at sodium, okay? Sodium is a metal, okay? And as I stated before, put in long-term memory, metals want to lose electrons, okay? And if sodium was going to lose an electron, guess what? It is going to lose that one little electron that's out there in the outermost shell. And when that happens, look what happens to the new valence shell. It has 8 electrons in the valence shell when it loses that one electron. So that's a driving force for metals. The same is true for calcium. Check out calcium. It's got 2 electrons in the outermost shell. If I lose those 2 electrons, then the next shell, number 3, becomes the new valence shell, which also has 8 valence electrons, that magical 8. Well, think about the opposite direction. Let me clear this up. For the nonmetals. The nonmetals have, in this example, chlorine has 7 electrons on the outermost shell. Now, from an energy perspective, it's not going to give up those 7 electrons. Okay, especially the fact that it just needs one more to fill up that P5 or the 3p orbital. Because right now it's carrying 6. And so by gaining one electron, it goes into that 6, 3p6. It's got room in the p orbits for one more electron. So that becomes the chloride. Okay. When sodium lost that outside electron, it becomes a plus. When calcium loses that outside electron, there's 2 of them, it becomes a +2. And the same is true for oxygen. Being a non-metal, it's going to gain electrons. Specifically, it's going to gain 2 because it's got room for 2, so that 4 becomes 6. Okay, that 4 right here becomes 6 because it can pick up 2 electrons and fill that up. And now by picking up 2 electrons, now it has a net -2, oxygen does. Look at all the, now look at the new valence shells. They all have 8, okay? And that is the driving force of why metals lose electrons and why nonmetals gain electrons. Because by doing so, they go into a more stable state, and that is an atom, or in this case, what we call an ion, with 8 electrons around, okay? Right, this picture here, which you have, I put it on the PDF of the PowerPoints, but this also shows you the electron configuration per element, okay? And as I stated here, look at 3D1, that's only when number 21 goes into place. We're gonna say from the first column to the last column, it's gonna go sequentially from D1 to D10, okay? You can see that it does hop around, okay? And that's beyond the scope of our class. And the same is true for the S. We're just gonna say from F1 to F14, even though it does hop around a little bit, okay? And this one, yeah, 5F. All right, so we're not going to do a lot of work with the F electron. Just be familiar with that there are F orbitals and then there are D orbitals. A lot of our work is basically going to stick to the S and the P's. All right. You can see here, everybody in group 1, this is group 1A, okay? What they share is 1 valence electrons, okay? All of them, notice that, 2s2, 2s1, 3s1, etc. And that's why they react very similar, is because of the number of valence electrons that they all share. Same is true for this group right here, okay? And that's all of the other groups. And that's why they have very similar reactivity. Notice that the noble gases have the orbits full, the p orbits full, and the s orbit full, and therefore explains why they are very unreactive. So what I'm showing here is using the periodic table and the position of the periodic table to quickly write the electron configuration, doing that method, or using the method down below, where that is the sequence that is given to you. And 1s2, 2s2, etc. Okay, keep it in mind if you do that, to remember that the 3sd won't come into play until if you do reach element number 21. Okay. All right. Did somebody have a question? I think they got their microphone on. I think that's you, Jonathan. Oh, excuse me. No, it's you. There we go. Okay, let me continue here. And as I stated earlier, your book uses the term happy. How happy they are, I couldn't tell you, but they're happy in the sense that their outermost shell has the magical eight electrons around it. So they're very stable, noble gases, that is, and very unreactive because they have 8 valence electrons already around them. And to lose one electron would take a lot of energy. And then to gain an electron for these noble gases would mean that they will have to put it in the next energy level, which is not a very, excuse me, stable position to be at. So that magical 8, with the exception of, excuse me 1 second, I'm having. Okay, I'm back. All right, so somebody's speaker's on. You might want to check your speakers. I'm picking up a lot of sounds. Jonah, I think it's you, Jonah.
No, I've been muted.
Oh, you have? Now I can hear you.
Yeah.
No, there you go. All right, now I went. There you go. Perfect. Thank you. All right, so that's the thing about noble gases. The outermost shell is full. I introduced to you the concept of the valence electrons, and those are the outermost shell. If we look at phosphorus, okay, phosphorus is this one right here, okay, 1, 2, and 3. So its electron configuration is 1s2, 2s2, 2p6, 3s2, and then it's in the third column of the P elements, 3p, 3p3, okay? The valence shell, there's 5 valence shells, which means that this phosphorus is in group Roman numeral 5a. Okay, there are 5 valence electrons. 3 of those 5 are in the p orbit and the other 2 in the s orbit, okay? Now, the big takeaway here is this. Phosphorus is a non-metal, and therefore phosphorus will gain electrons, okay? The p orbit has room for 3 electrons, okay? There's 5 valence electrons, so from a energy perspective, it needs 3 more to become stable, which would be the optimum thing to do. And that's what happens when phosphorus gains electrons. That P, this is phosphorus. And then when it picks up 3 electrons, this becomes 6. And then by picking up 3 electrons, it becomes phosphide. Okay, that's the ion. We change the name for the nonmetals, their name gets changed from whatever its name is to the IDE ending when it becomes ion. So oxygen becomes oxide, phosphorus becomes phosphide, sulfur becomes sulfide, and you have fluorine is fluoride, chlorine is chloride, etc. Okay. Right. So this is where all what's happening. The valence shell is where all the action happens. That's where all the chemistry happens. And then either something's going to happen, I'm going to lose electrons, or we're going to gain it, whichever. It depends on what the element is and the conditions, and therefore get into a more stable state than it is just sitting there with empty shells. Okay, orbitals, I should say. So the question here is to determine, well, how many valence electrons does it have? We can easily go, like I introduced, is find the element and product table, go up to the group number, and that tells you, okay? Or if you're not sure about that, then do the full electron configuration, okay? So chlorine has 7 valence electrons, which are occupied in the 3rd energy level. 5 of them are in the P, 2 of them are in the S. Guess what? It's a non-metal. It will gain electrons because, and it will gain specifically 1, because that P orbital is not full and needs 1 more to become P6. Right on. Beryllium has 2 valence electrons, okay, which are is in the 2A group, and chlorine was in the 7A, Roman number 7A. Aluminum has 3 valence electrons. It is in the Roman numeral 3A group. Okay, those 3 valence electrons are, 2 of them are in the S, and 1 of them is in the P orbit of the 3rd energy level. Okay. All right, and so the driving force here, guess what, is for aluminum, by losing those 3 electrons, the next energy level in the new valence shell is the 2nd energy level, which has 8 electrons around it. Okay. All right, so going across the product table with respect to the group number, the Roman numeral number also corresponds to the number of valence electrons. Not only that, the additional information you get from the periodic table is as follows. Okay. Now, the group 4 elements, of which, for example, carbon is in, think of it as being on the fence. Those elements, 1 or 2 things can happen depending on the reaction conditions, because since they're on the fence, since their valence shell has 4 electrons, it can either gain 4 more to put it more in a better stable state, or guess what? It can lose 4. Which direction it goes depends on the conditions, the reaction conditions. So the result is this: those elements in group 4 can have a charge that can vary from a +4, and that is because they lost those 4 electrons, all the way to a -4, because they gained 4 electrons to get that happy 8, okay? Those elements, specifically the metals, before group 4, they want to lose electrons. So everybody here is losing electrons. Specifically, group 1 will lose 1, group 2 will lose 2, and group 3 will lose 3. When they become ions, you end up with a +1 charge for the elements in group 1, a +2 charge for the elements in group 2A, and a +3 charge for those elements in group 3A. Okay, think about it. If I have 3 valence electrons and I lose them all, I lose 3 negative charge species. Okay, now I have a net +3 charge. Okay. Starting with group 3A, they have 5 valence electrons, and then going across 6, 7. Now we just established nothing's going to happen with the last one. You're stable. They don't want to do anything else. The group 5A elements will, for example, gain 3 electrons, okay, resulting in a -3 charge. In gaining 3 electrons, now they got that magical 8. Moving over to the next group, they're going to gain 2 electrons, and they're going to end up with a -2 charge, because 6 + 2 is 8, right? And so seven, the group seven, they're going to gain 1 electron. So everybody in that group will gain 1 electron to get that magical 8. Okay. And so those species with the charges are what we call ions. Ions are nothing more than the elements that, depending on the type of element, have either lost or gained electrons. Okay. What we have here is that the metals always will lose electrons and always will have positive charge. The non-metals will always gain electrons and end up with a negative charge, okay? The non-metals. So that group number helps you to tell you how many valence electrons it has, will help you to tell you how many electrons it would either lose and how many it might gain, depending on the element, and also tell you, obviously, what the new charge is, depending on the group number. Okay. So yeah, pay attention to the group that it's in. It'll give you a lot of information. All right, valence electrons for these is we simply just go find them on the periodic table. Strontium SR is a group 2A. Okay. And so it has 2 valence electrons, just like everybody else. That's element number 38. Okay. Bromine is in group 7A. Okay. The argon, which is a noble gas, is in group 8A, and silicon is in group 4A, Roman numeral 4, and then finally the last one, sulfur, is in group 6A, Roman numeral 6. Okay, so not necessary to memorize those numbers specifically. All you got to do is find them on the periodic table, okay, and then find what group they're in. All right. Now, the question here is, why do atoms make compounds and why do they bond? Well, the driving force, like I stated, is to lose electrons to get to that happy 8. Now, there's going to be 2 types of compounds that we're going to, of all the chemistry involved here, there are going to be 2 types of compounds. One of them are ionic compounds, in which these elements have lost or gained charges. So we end up with a positive ion or negative ion. And the driving force to make compounds is the positive and negative attract. They're going to attract to each other to make a compound. They're not going to bond with each other, but they're going to attract to each other like 2 magnets because of the positive charge and negative charge. Then there's a second type of chemical compounds that we deal with that want to share electrons, and actually, when they form a bond, share these electrons, and they're not separated. They're hooked up together. Okay. Now there's equal sharing and unequal sharing, and we'll have a lot more to say about that down the road here. And so, but in both cases, the ultimate goal is to maintain or to obtain that octet rule or the duet rules. Hydrogen will always have the duet rule, will always have 2 electrons around it when it's bonded to something. Everybody else will always have 8 electrons around it. Okay, and that's what basically what I just explained there. To create atoms will create ions to maintain them. So what is happening here? Well, let's take a look at the electron configuration of sodium, which is 1s2, 2s2, 2p6, and 3s1. The valence electron is in the 3rd energy level. Okay, so it has 11 protons and 11 electrons as an element. So the net charge, the net is equal to 0, right? I got 11 positives, 11 negatives, they cancel each other out. Now, when it loses the electrons, and now that 1 electron, because it is a metal. Remember, sodium is a metal. It will always lose electrons, and it's going to lose that electron in the outermost shell. And now its new valence shell is in the second energy level, of which they now have 8 electrons around the outermost shell. It does now have a total of 10, so it didn't lose protons. It still has 11 protons, but now it has 10 electrons where it started off as the atom as 11. That results in having 11 positives, 10 negatives. My net charge now is a +1. So this is the ion that is generated. Okay, not to be confused with the element, which has a 0 charge. Two different moieties here, two different species. Okay, the ion has a plus charge. The atom has a net 0 charge. All right, now let's take a look at sulfur. Sulfur has 6 valence electrons. 4 of them are in the P of the third energy level, and 2 of them are in the S of the third energy level. Okay, they're highlighted there in yellow, dark yellow. Valence electrons. Now, sulfur is a non-metal, and non-metals want to gain electrons. Specifically, sulfur is going to gain 2 electrons because there is space, there's room in the p orbits for 2 more electrons. Okay, it's got 6, and you ask yourself, well, it's going to take a lot of energy to get rid of 6, and not so much energy to add 2 to it. So it's a non-metal, it's going to add 2. Okay, and now its electron configuration now is in valence shell would be 3s2, 3p6. Again, the magical 8 has been obtained. There are 6 valence electrons for the ion right here, okay, which now is in a lot more stable state than being an atom. Okay. Furthermore, its name went from sulfur. Here is sulfur. When it becomes the ion, it is sulfide. IDE. That is the ion. Sulfur is the atom. Big difference with respect to naming. Okay. All right. Now here we're asked to write the electron configuration. And I see the big mistake I see in these type of questions is what we did before. We were doing the electron configuration of the atoms. Okay. Here, sometimes students fail to read the question and write the electron configuration for potassium element. But this is +1, so we want the element. We want the ion, not the element. Okay. If we were doing potassium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Note the difference between the atom and the ion. Okay. When it became an ion, it lost that 1 electron. So when you write the electron configuration, make sure you read which one you're doing, either the ion or the element. Okay. And that's false. Now what they've added is this. Argon has 18 electrons. And there are 18 electrons. And so now potassium, by losing 1, now has 18 electrons. Okay. What's happened is potassium ion has the same number of electrons as argon. Okay. I didn't say that potassium ion became argon, okay, or argon became the potassium ion. That's not what it said at all. They share the same number of electrons. Remember, for potassium to become argon, potassium would have to lose a proton, okay, which is in the nucleus. Remember, the protons define what the element is. All right, so no, they just share the same number of electrons. And what that means, they have a term for it called isoelectronic, meaning that they have the same number of electrons, isoelectronic. So the potassium ion is isoelectronic with argon. Nitrogen, which now becomes nitride, the nitride ion is isoelectronic with neon. And the magnesium ion is also isoelectronic with neon, okay? Both the nitride and the magnesium share the same number of electrons with neon after they become ions. Obviously, when they're the atoms, they're not sharing anything, okay? They have a totally different number of electrons. So in this case, I did introduce a topic already about ionic charges, and by knowing what group it's in, by knowing if it's a metal or non-metal, you can very quickly determine what is the anticipated charge. So group 1A would end up with a +1 charge, okay? Whereas group 2A will end up with a +2 charge. Group 1A has 1 valence electron. Group 2A has 2 valence electrons, and they happen to be where the metals are, and metals lose electrons. Okay, group 3A will end up with a +3 charge. Now, it doesn't make a difference how you write it. For example, it could be written as +2 or 2+, tomato, it's the same thing, as long as you got a charge up there, okay? It does make a matter if you mean to write negative and you left it as positive, it's a totally different ballgame. Okay? In other words, is this: you won't find a non-metal with a positive charge, nor would you find, at least in Chem 130, would you find a metal with a negative charge. Okay. All right, group 7, starting at 7A, they are nonmetals who end up with a negative charge because they pick up 1 electron. Group 6 will end up with a -2, so forth, okay? Nonmetals want to gain electrons or anions, and therefore group 7A will have a -7 charge, just like I showed you earlier on that scale, on that few slides back. The respective charge that they would be depending on the group, okay? And you might think about, look, I got 7 valence electrons. If I pick up 1, I got the magical 8 for group 7. 6A, I pick up 2 electrons, I got an overall -2, I got the magical 8 again. And group 5A has 5 valence electrons. So if I pick up 3 electrons, I got a -3. And again, all of them will have 8 electrons. Okay, 8 electrons around them by gaining 1, 2, or 3 respectively. Okay, metals, as we know, want to lose electrons. I can't overemphasize that. They become cations. That is the name for metal. Up to this point, we've been talking about, ions. Well, that's the general name. Specifically, metals become cations and nonmetals become anions with a negative charge. Group 4, as I stated, were carbons in there, for example, and silicon. These moieties, depends on the conditions, they can vary from ±4, depending on the conditions, okay? Group A, nothing's going to happen to them. They already have 8 valence electrons. They are happy, quote, quote unquote, happy, stable, and they're not going to give up their electrons readily. Okay, so those are the respective charges going across the periodic table. I cannot overemphasize that this is a true statement for only those elements, A elements, okay? Those are the ones for these and these, yeah, okay? -1, -2, -3, and excuse me, +1, +2, +3, okay, and then everybody else here, this can go +4 to -4, and then everybody else over here goes from a -3, -2, -1, okay? Those are the ionic forms. Now, with that being said, and this is crucial to remember, because it goes on to when we start naming compounds in the nomenclature, which, by the way, if you haven't had a chance to at least attempt the nomenclature, go in there and you have unlimited attempts. I want to refresh your memory. Yes, there is a due date there, and that the due date is the last day of class. Okay, please don't wait until the last day of class. It is 10% of nomenclature. It is 10% of your grade. Now, if you're in the middle of the grade scale and that 10% makes no difference, obviously that's your choice, okay? I mean, it's your money. You do with it what you want. But if you're on the border, let's say you're on the border of the A, bottom layer of the A, bottom half of the A, okay? Once I put a 0 in that 10%, that A can easily become a B. On the same token, that B plus can easily become an A, depending on where you're at, okay? I've not put zeros in there. I've only had one student attempt it now. They did a decent job. Unfortunately, you remember, you got to get that 80%. 80% and above, you keep the score. Anything less than 80% and this shoots it back to 0. Okay, so I believe next week or the following week, I'm going to start going in there and putting in zeros. And I do that for a reason. And that's because your grade right now is not really, quote, the true grade, because it only incorporates those assignments that have been graded. Okay. And so by putting in a 0, you can actually, it would give you your true standing of where you really are at. In the past, I waited until a week before the semester ended. I think I stated this before, but we're getting close to that time, so I'm telling it again. I waited until about a week or 2 before the semester ended. And then people went along the semester thinking they were okay, they're happy with the grade, but as soon as I put a 0 in there, it dropped it to a level that they weren't happy with. And now you only got a week or so to try to get that grade up on that exam. So people were rushing to try to get it up there, and I don't want to put you in that position. So that's why I put a 0 on it way early in the semester. So you have all semester, the rest of the semester, to do as many attempts that you can, and get to the point where you're comfortable with the grade that you want. Or make that 80% for sure, and you can still continue to get it higher if you want for that nomenclature you have. Okay, so having said all that, let me go back to the elements here that are circled. Now, we've been talking about ions. Now, there are certain ions that have a constant exact numbers. We talked about during the conversion factors and so forth. These ions have an exact charm, okay? And I circled them. There's 16 of them. I call them the sweet 16. Okay, all of them are metals, obviously. Okay, now everybody in group 1, right here, all the metals, starting when I'm just talking about the metals, everybody in group 1 will always have a +1 charge, 100% of the time. Everybody in group 2 will always have a +2 charge, and they become ions. Okay, they lose the electrons they're metal. And so what we have there is 1, 2, 3, 4, 5, 6. There are 12 elements that you know 100% of the time what their charge is. Now, on top of that, we're going to add 4 more to give us a total of 16, otherwise known as sweet 16. Okay. Aluminum always has a +3. Zinc, Cn, always has a +2. Silver, Ag, always has a +1. And Cd, cadmium, always has a +2. So those 16 elements, 100% of the time, you know their particular charge when they become ions. That means that everybody else, all the other elements, their charge varies. For example, copper, you have copper 0, which is the element, but also copper can lose 1 electron to become copper +1, but it can also be copper +2, okay? Iron, for example, could be iron 0, the element, but it can become iron +2 by losing 2 electrons, or iron +3. So we can't predict for these metals here like we can for the sweet 16. And that's going to be important when we start naming these compounds, okay? All right, so put the 16 in your long-term memory. All right. On the same token, with the anions, you always know their particular charge, okay? Because the nitrogen becomes nitrite, always has a -3. Phosphorus will always have a -3. Oxygen will have a -2. Sulfur, -2. Fluorine, -1. Chloride, -1. Bromide, -2. Iodine, -1. Those guys, 100% of the time. Selenium or selenide, -2. Okay. First of all, their names get changed, and you add the IDE suffix. So sulfur becomes sulfide. Okay. Not to be, for example, sulfur becomes sulfide, not to be confused with this down here, where you see the suffix of ate, sulfate, sulfite. Those guys deal with oxygen. We'll get to those in a while. But right now, the IDE talks about a single element by itself gaining electrons. And those are going to know 100% of the time their particular charge. So now you know the cations, you know the anions. I tell you this because when we start writing compounds, we need to predict what the partner either of the cation is or the anion is. And you're always going to know one or the other to calculate what the charge is for the partner. Okay? You will know that. Okay. We'll come back to this. Let me finish this up and then go take a quick break and we'll be back. All right, so for the charge itself, what we do to find that out, we look at lithium. Lithium on periodic table is in group 1. When it becomes ion, it's a metal. It will lose electrons. Being in group 1 will be a +1. Magnesium also is a metal. We find it in the periodic table, it is a +2. So it would lose 2 electrons to become the ion, and that becomes magnesium +2. Sulfur, like we just talked about, it is in group 6, meaning that it's a nonmetal and it will gain 2 electrons to give us a sulfur -2. Bromine is in group 7, will gain 1 electron, give us a negative charge. Nitrogen, being in group 5, will gain 3, like the phosphide did. And then aluminum is one of the sweet 16, will always have a +3. Now, what we're starting to do is we're going to start putting compounds together. We're going to start putting the cations and the anions together. So that means that I can take lithium ion and bond it to the bromide, okay, or the sulfide, or the nitrite, okay. I can also take a magnesium and bond that to the sulfide, or I can bond that to the bromide or the nitride, you know, and if I had the sulfide and all the other combination, I can do that. And then aluminum, I could do the same thing with aluminum, meaning that I can take aluminum and bond that with the nitride or bond that with the bromide or the sulfide. So I'm slowly starting to build up, hopefully you can start building up a database of compounds that you can mix and match with. There we have all these metals, they become ionic, positive charge. And then we have all these non-metals that I've just marked off on the calendar, plus all of the polyatomic ions that you see on the periodic table on the bottom left corner. And we can do a big mix and match, okay? Positives attract the negatives. And we're gonna learn how to put enough of each so when they come together, the net is zero. We're gonna have to put enough cations plus enough anions to give us a net zero. Okay, so put this in memory that when we make compounds, when we're starting to make compounds, and that's shorthand for compounds, that the number of cations plus the number of anions, when we put them together, must equal zero. Okay, so that means that if I take sodium ion and I get the chloride ion, when I put them together to write the formula, I put them together 1 to 1. Got one positive, one negative, they cancel each other out. So the formula for sodium chloride will be NaCl. That's simple. Okay? That's simple, but sometimes you got 2 to 1 or 2 to 3, 3 to 2. We'll have a technique there, process to show you how to do that. All right, so here's the term isoelectronic. That's important because we're not saying here that the ions become the other atom. That's not what we're saying. We're saying that the magnesium ion is isoelectronic with neon. They share the same number of electrons only. Then the phosphide is isoelectronic with the argon. We can very quickly use the periodic table to even answer that question, because the way it amounts to is this, that if we look at potassium, for example, which is right here, when it becomes ionic, it's going to lose an electron, and it's going to be isoelectronic with the metal, excuse me, with the noble gas behind it, okay? Potassium has 19 electrons. When it loses that one, now it has 18 electrons like argon, okay? And so for metals, when they become isoelectronic, become ionic, they become isoelectronic with the noble gas behind it. For non-metals, they become isoelectronic with the noble gas in front of it, okay? So for example, I just said potassium becomes isoelectronic with argon. Chlorine, by gaining 1 electron, now has 18 electrons like argon, so it becomes isoelectronic like argon in front of it. And so for non-metals, when they gain electrons, they become isoelectronic with the noble gas, in the immediate noble gas in front of it. Okay, so and that's true for phosphorus, sulfur, and chlorine. They all become, when they gain electrons, they become isoelectronic with argon. For nitrogen, oxygen, and fluoride, they become isoelectronic with neon. Okay, that is what they're talking about right there. All right. Here is the electron configuration for specific types of ions: calcium ion, the oxide, the chloride, and the aluminum ion. Okay, and that just here shows you which are noble gas they are isoelectronic with. I cannot overemphasize the calcium ion did not become argon, nor did the oxide ion become neon, nor did the chloride ion become argon. Okay, they did not do that. they become isoelectronic with those particular noble gases, simply because they share the same number of electrons. All right, here's another table that should look somewhat familiar. They're talking about selenium, which is element number, senior moment here, number 34. Here's 34 here, 34 here. And you got aluminum 13 and aluminum 13, okay? And so they want to know how many protons selenium has, either in the form of the atom or the ion. Well, obviously, they're both going to have 34, okay? Nothing was lost here. No protons were lost, nor were any neutrons lost. What changes is the number of electrons, okay? It's a non-metal, so he picked up 3 electrons to form the -2 ion. Same is true for the aluminum, which has 13 protons, either as an atom or as an ion, okay? They're going to have the same number of neutrons before and after, and where they differ is the number of electrons. So they lost 3 electrons, and now it has 10 electrons when it is an ion. All right, with that, ladies and gentlemen, that brings me to the end of this chapter, chapter 5. And what I want to do is take maybe a 10-minute break. And then we will jump into chapter 6, which deals with the periodic table. And it's fairly quick. A lot of this information we have here we talked about before I've introduced it to you. So I got 307. Let's come back about let's say 3. Okay, go make it 315. All right, we'll make it at 315, and we'll be back. Okay, I am back. All right, this particular chapter, it deals with the periodic table. Some of the topics we've been talking about already. We kind of introduced that already. So it's just a little bit extra detail. All right, let me introduce you to this particular scientist. Okay, interesting looking character. Anyways, Dimitri Mendelee. Back in 1869, he's credited to actually creating the first periodic table. So based on his observation of the elements known at the time, he created this table, put them in an order of increasing mass, and then within the same column, put them in the same column, those elements that exhibited similar properties. Unbeknownst to him, as we learned later on, that is because they share, everybody in the same column shares the same number of valence electrons. But one aspect about his table, that there were some empty elements there that predicted that that's where an element should be. And sure enough, a lot of scientists proceeded to go search for them. And I actually found the missing elements of his table. Another scientist by the name of Mendelee, what he did is rearrange the elements to the table that we're more familiar with now. And he put them in order of increasing atomic number, okay? Then also brought forward the periodic law that elements in the same column have similar properties. Again, because they share the similar type of, the same number of valence electrons. Now, notice that's the table that we normally are all familiar with, and it's been around for a long time. And generally what happens, if you notice, here's number 57, and then 58 is right here. Okay, here's number 89, and then number 90 is right here. So what's happening is these in here, which have their own little name we're going to learn about, actually belong right in here. So if we were to take the periodic table and spread it out, it should really look as that. And those are the green one, or the F block. Okay, these are the F block. Here's the S block. Here's the P block, and there's the D block. And that is the spread out element. Well, kind of hard to read and everything. It's not very, I don't know, it's just been compact. Okay, and that is the periodic table that we have now. Now you see the numbering sequence on top, 1 through 16. That is the push now to go with the different, get rid of the Roman numerals and come with the numbers 1 through 18. A lot of pros and cons about that. The Roman numerals, you get a lot of good information with Roman numerals, not specifically how many valence electrons you have there. So anyway, you'll find some periodic tables with numbers 1 through 18. Some still maintain the Roman numerals, and some maintain both. Now, there's been a variety of different types of periodic tables that have been proposed, and here's one is circular periodic table. It really didn't take off very well. And there's another one that's been proposed, which is pretty interesting because what it does predict the whole section here of what are called superactinides. There's a whole prediction of future elements, which there are scientists currently trying to get elements above 118. All right. Anyway, Niels Bohr, as we talked about last chapter, proposed the idea and brought forward the idea that electrons occupy specific energy levels. And then here's the S block, the D block, and the P block, and F block, all related to the electronic configuration and the electrons and where they exist for all of the elements. Okay. Now, the horizontal row is called the period, which is the term I've utilized. It's also the energy level. There's 7 of them. And the vertical rows or columns, I should say, are called groups. You also will hear the name family being in the same family. So elements in the same group exhibit similar properties. Again, because the number of valence electrons they share. Now, there are the main group elements, and those are the ones with the Roman numerals followed by the letter A. And then there are what are called the transition metals, okay? And so the main group elements are from 1A, 3A across through 8A, and then the transition metals are the ones in here and including these, okay? All right, now some of these have even more specific names which we're going to touch on. So we got the main group elements, which are the A group, and then what are called transition metals, which are the B group, okay? The periods or energy levels, different periods. We talked at length about those, okay? And then the groups, the columns all exhibit similar properties. We also spoke about that. Now, the certain groups have a more specific name. For example, group 1A, right here, they have a special name called the alkaline metals, except hydrogen, obviously, because hydrogen is not a metal, it's a gas. And then the group 2A, the next one in, are called alkaline earth metal, okay? And then the halogens over here, group 7A, starting with fluorine on down, they're called the halogens. A lot of the old lights, headlights in cars had halogen lamps, okay? And then the last column, obviously, that name we've already talked about, they're called the noble gases. So we have the alkaline metals in group 1A, the alkaline earth metals in group 2A, halogens in group 7, and noble gases in group 8. Those are specific names for those groups, okay? Now, we talked about the transition metals. Now, we have 2 types. We have the inner transition metals here listed in what is these I circled, and then the green ones are the transition metals, or the D block, if you recall, and the F block elements. Now, the inner transition metals, because normally they're in here, these groups, they have their own little additional names. So group 6 are called the lanthanides, period 6, I should say, are lanthanides. And the last group is starting here with 90 are called the actinides. Okay, so here's the inner transition metals. The lanthanides are also given the name as rare earth metals. Okay, a lot of them are used quite a bit in electronics and so forth. And then the actinides are all of them are radioactive material. Normally, what's happening here is that the elements from 93 forward are actually man-made, and they take particle accelerators where you get matter just busting into each other and creating new elements. So they use these particle accelerators to make these elements, and all of them are radioactive, unstable, don't last very long. Hence, if you recall, the atomic weight is written in parentheses. They got parentheses in there because we don't have a really accurate number for them. So you may get questions like, all right, the alkaline metal of the third period, okay? Well, we go to the third period, 1, 2, and 3, all right? And they're talking about the alkali metal, okay, which would make it the very first one, the alkali, group 1A, so that should be sodium, okay? All right, the halogens are the ones in group 7, and we're talking about the second period, so that'd be 1, 2, that must be fluorine, okay? And then finally the noble gases, which are the last group, group 8A, and you're talking about the fourth period, so that's got to be krypton. All right. Refresh your memory on this slide where we talk about metals, nonmetals, and metalloids. Okay, that's really going to help us out down the road when we start talking about compounds and what type of compound they are, being ionic or covalent compounds. We'll talk at length about that. Okay, with respect to the radius, that is the distance between the center of the nucleus and the outermost shell. You can hopefully deduce already that going down the periodic table, we're getting larger energy levels, energy level 1, 2, 3, all the way to 7. So obviously, as we go down the periodic table, the elements get bigger. Okay, so the trend is element radius increases as we go down a column. Okay, now where they differ is going from left to right within the same period. Going from left to right, what is happening, there's a couple of things happening. Let's take, for example, if you want to compare the radius of carbon versus, let's say, fluorine. Well, the difference between carbon and fluorine, they're different elements, obviously, but we got 6 protons for carbon and 9 protons for fluorine going across the same period. They're both in group 2. They also have 6 electrons and 9 electrons respectively. So fluorine has more proton and electron interaction, more nuclear force than carbon. The result is more nuclear force pulls those electrons and the shell in closer, resulting in the radius of the fluorine to be much smaller than the radius of carbon. And that's the same trend throughout the periodic table, going across from left to right within the same group, that the elements on the far right, as you go across the period, they get smaller in diameter versus the previous element of the same period. And it's simply because they got more nuclear force going on, and those electrons are being pulled in closer into the nucleus. okay? The positive charge increases, electrons are pulled closer. So you can see the trend is this. This helps you out maybe with the snowman. That is, we go down the periodic table. Obviously, the radius gets bigger. And take that snowman, turn them on the side, and that as we go from left to right, the radius gets smaller because the nuclear force gets greater when we go from left to right, and when we're going from top to bottom, we're just increasing our energy levels with that particular element. So they're just getting bigger. Okay, so the general trend is shown here. You can see how the size decreases going from left to right and top to bottom. Obviously, you see some exceptions to the rule, but like I stated, nothing in science is 100%. There's always a little exceptions here and there. Okay. All right. So you may be asked the question, all right, so we want to compare these three elements. The question is, which one is larger? Well, to answer that, we look at the elements that were given and we find them on the periodic table. Now, when we do that, fortunately, we find them all, they are all in the same group. So we are basically going down the periodic table. So it stands to reason that the bottom one is larger, okay? It is larger because its valence electrons are in a larger energy level. Okay. Now, the next set is these three here. And again, we find them on the product table, and here they are. They happen to be in the same group. So we're going from left to right. And so sulfur has a lot more protons than the other elements, a lot more electrons, so they have a greater nuclear force, resulting in, for sulfur, those electrons are being pulled in much greater, okay? Much greater force, resulting in a smaller radius for sulfur. And magnesium and silicon are much bigger with respect to the radius. Okay. Now, you might be asked questions like this, and you'll be told in the question, don't just quote the trend that you observe, but explain the reason behind that trend is the question. Why is the radius getting smaller going from left to right? Why does the radius get bigger going from top to bottom? Okay. There are some videos. Check the module, which Dr. Kim has re-recorded. So feel free to read about those on top of what I record here. So it'll give you a lot more information. Okay. We're going to talk briefly about what is called ionization energy. Okay. What this is simply a measure of the amount of energy necessary to remove an electron from a neutral atom. Okay, that's the important part. We're taking a neutral atom, an element, and we're hitting it with some energy, and the idea is to remove an electron and to see how much energy it takes. So the process here is we have the element, and then after it's done, we have generated an electron and formed an ion. Okay. Now, think about what we've been talking about. I just stated, put in long-term memory. Metals want to give up electrons, non-metals want to gain electrons. So that would suggest that metals easily give up their electrons, right? As compared to non-metals that they're holding their electrons on very tightly, because if you go from left to right on the periodic table, the number of protons increases, the number of electrons increases, and that nuclear force increases. So those electrons are being held on much closer in the same period than those on the left side of the period, which tends to go into the metals, okay? So we would anticipate the ionization energy for non-metals to be much greater than for metals. We can anticipate that, okay? All right. So the trend is this: the ionization energy within a group increases. Okay, what does that mean? Okay, let's look at the periodic table. That if we look at, let's say lithium versus potassium. Now, lithium has 3 electrons, potassium has 19 electrons. Okay, What they both share is this: they got one valence electron sitting out there in the energy, in that outermost shell, the valence shell. For lithium, it's in the second energy level. For potassium, it's in the fourth energy level. And so the result is that that one solid electron for lithium is much closer to the nucleus than that one lone electron for potassium, which is 4 energy levels away. So I would anticipate that the amount of ionization energy for lithium would be greater than for potassium, because in potassium's case, its electron is further away from the nucleus and there's less attraction, less force occurring. Okay, so that explains why going from bottom to up, the ionization energy increases. Okay. The other trend is that it increases from going from left to right. Okay, left to right. Again, for the same reasoning, is that the radius gets smaller as we go from left to right. There's more proton force, nuclear force on the right side. So those electrons are being held down tighter than the ones on the left side. Plus, as we go across the periodic table, we're reaching the realm of nonmetals compared to metals. And metals want to give up their electrons much more readily than nonmetals. That's another fact. And then obviously you can anticipate that the noble gases are really going to fight to not give up an electron. Why? Because they got that magical 8 going on for them. And it's going to take a lot of energy to pull one off. Okay. So we're going to anticipate that the neon gases are going to require much more energy than the rest of them in general. Okay. And that could be seen here in this particular graph. If we start off, if we look at the scale on the left-hand side is a measure of energy. And then down here is the x-axis is the atomic numbers going across the periodic table and the amount of energy it takes to yank off an electron. If we start off with hydrogen, which is right here, we got about, I don't know, about 13 units ballpark, 13 and a half units of energy. That's in hydrogen, left-hand side of the periodic table. Now, as we go across over to helium, my goodness, the ionization energy to yank off an electron from helium goes up all the way about 24. That's a big jump, almost a jump of what, 11 units of energy. Okay. Now, once we pass helium, we go back to the metal, which is lithium, which is right here. This is lithium right here. And this is going across period number 2, going from lithium all the way across to neon. Well, as I stated, as you go across from left to right, proton electron interaction increases. So electrons are starting to hold their electrons, atoms starting to hold their electrons even tighter. And then when we get in this particular region, we get into the non-metal region. So those guys are really going to fight to keep their electrons until we hit neon, which you can see the energy somewhere about 22 units. All right, so after neon, okay, we go across to sodium, and the energy again drops to the same level that lithium was. And we go across from sodium all across to argon. You can see that to go across the periodic table, the energy increases. Not as drastic as the second period. This is the third period right here. Third period, second period, and this is the first period. Not as drastic as the second period, but keep in mind that as we go down the period, we're getting to become bigger elements. And as we get to bigger elements, those electrons on the outermost shell are interacting less with the nucleus. Okay, there's less force holding on to them. You get to the fourth energy level, you can see, which is potassium, going across to krypton. The slope of that line starts to get smaller. And eventually you can get to the point where that energy difference is minimal, okay? Because again, we're getting into big elements, and those electrons, regardless if they're metals or non-metals, they're just further away from the nucleus, so it's not going to take a lot of energy to back them up. Okay, but the trend is still going across the product table is an uphill trend. Okay, more energy as you go from left to right. You remove an electron. All right, so that is called ionization energy. Okay, that's the amount of energy necessary to remove an electron from a neutral atom. Okay, so you might be asked questions about, again, like we're talking about radius earlier. I got three elements here. Which one have the highest ionization energy? Now, you can do this in two ways. One, find them on the periodic table. Once you do that, realize that they're in the same period. Okay, here you got magnesium, here's aluminum, and here's chlorine. And given the trend that we have, because the chlorine is smaller, the electrons are held on tighter, chlorine's going to take more energy. Makes sense. But furthermore, guess what? We're comparing two metals with a non-metal. Just that in itself should tell you that the chlorine is going to require more energy to remove an electron than the others, because chlorine wants to gain electrons. And the others are metals that want to give them up. Okay. The next set, we find them again in the periodic table. This time they're all in group one, so they're going down the periodic table. And the question is, who's going to have a high ionization energy? But that would definitely be the one that is smaller, which would be lithium. Why? Because that electrons, these guys all happen to have one valence. Like that one electron is closer to the nucleus for lithium than it is for the bigger element RB. Okay, so higher ionization requirement energy for lithium because it's smaller and it's holding on to its electrons a little bit tighter than the larger one. Okay, all right, don't forget there's also videos concerning ionization energy, okay, from Dr. Kim. Feel free, obviously, to read those and listen to those, I should say, give you an alternative source. Now, this particular property, now don't confuse this, which is called electronegativity, with IE, ionization energy. The difference is this: electronegativity, which is a property that's going to come across over and over and over and over again, okay, throughout the semester. Electronegativity is a measure of the ability of an atom to attract electrons onto itself while it is bonded, okay? While it is bonded. And this is what we mean. Let's take a very generic bond. Now, what we do that is let's take A is some element, and we'll just have it bonded to another A. We draw this line here to represent two electrons, okay? Two electrons that are being shared between the atom A of each one. Now, since A and A are the same, whatever element it is, that sharing of that electron is equal, okay? We call that equal. Now, if I were to replace that A with B, which is a totally different element, now what's happening is we get unequal sharing. One of these over here we got equal sharing. It's like a tug of war where I got two people, two 200-pounders pulling on that rope, and it doesn't go anywhere because it's equal pull, equal strength. Now I have an unequal example where I got a 200-pounder and a 400-pounder having a tug of war. Obviously, just by the weight of the 400-pounder, he's gonna pull that rope onto itself much greater. And that is what we call about electronegativity. That 400-pounder will have a higher electronegativity and pull the electron source. It's not going to break it, but it's going to pull the electron source, electrons away to it. And we'll have an unequal sharing. To determine who is pulling more, we use every element has an electronegativity value. We don't have to memorize all the values, it's not necessary. We just got to remember that one, fluorine is the most electronegative element in the periodic table, and that is our benchmark. And so when we want to do a comparison, if we see fluorine in anywhere in the model, unless it's bonded to another fluorine, that means that fluorine will have the pull. It's going to be the 400-pound of pulling the electron source onto itself. But if we have, let's say, a carbon and nitrogen bond, we may be asked the question, well, who's pulling those electrons onto itself greater? We have to determine who has the higher EN. Well, we go to the periodic table, and carbon's about right there, nitrogen's about right there, okay? And we find the position there in relative to fluorine. Whoever is closer to fluorine has the higher electronegativity. Nitrogen is closer to fluorine, therefore nitrogen has the higher electronegativity. And so nitrogen in this particular example would pull the electrons in that bond closer to itself, okay? And creates a special type of bond, okay? Which then affects the properties of the overall molecule that then we can take to do a comparison with another molecule to determine if it has a higher boiling point or some other physical property. We're going to be able to determine, looking at two different compounds, to determine which one would have, say, a higher boiling point based on the type of bonds they have, okay? And that is based on the electronegativity, okay? Because we have two types of bonds. We're going to discuss at length in the next chapter. We have a type of bond that is a combination of a metal and a non-metal. Okay. Let's, for example, sodium chloride, table salt, what we put in French fries. We have a metal, sodium, interacting with a non-metal, chloride. Now, these are ionic compounds because sodium became an ion to form ion plus, and chloride has a negative charge, okay? If we take sodium chloride and we put it in water, they will break apart. They dissociate. In fact, all of these ionic compounds will dissociate, okay? Because what they are is not really an ionic bond. They call it an ionic bond, but it's really an ionic attraction. It's like two magnets coming together, and they're not sharing anything. Like I'm overlapping my fingers. They're attracted to each other because of full positive and full negative charge. And when you put these in water, for example, they will break apart, dissociate. Sometimes, depending on the ionic compound, some of them dissociate 100%. Some dissociate maybe 95%, but nevertheless, all dissociate to different degrees, okay? When we have a non-metal combined with a non-metal, like this carbon-nitrogen example, we end up with what we call a covalent bond or covalent compound. In that scenario, there's actual sharing of electrons between two of these atoms. And if we were to put these in water, they certainly will not break apart. They will remain intact, okay? And they don't dissociate. They don't have a full charge. We're gonna have a lot more to say about those in time, trust me. But it all gonna come back to this electronegativity. If it wasn't for a difference in electronegativity in a bond, it'd be very difficult to make new compounds, to make new medicines, to make new products and so forth, because because the difference of electronegativity allows us as chemists to synthesize certain compounds. Otherwise, without it, it's going to be very, very difficult to make new compounds. But it's very important thing about chemistry, this electronegativity, and it has a big effect on the properties of the molecule. All right. So we know that noble gases don't have electronegativity, of course, because they don't form bonds. They got that 8 going on, except for helium, which has that 2 going on, and they're not going to react. They're not going to give up their electrons very readily, so they're very inert. Okay. That being said, congratulations, we are done with chapter 6, and what we got? 10 more to go. Okay. Actually, we got a couple of chapters are like maybe 10 slides. They're very, very short. All right, so 5 and 6 are done. And then we stop and we're just all right. In fact, we ended up a little bit early. All right,